Welcome back to day 2 of Riemann sum. In this video, we're going to look at a trapezoidal sum to approximate an integral. This is page 11 in your notes. Okay, on yesterday, boys and girls, we learned how to use Riemann sums to find the area under the curve. Today, we're going to find a new method, which is called a trapezoidal sum. So let me just give you a little background on trapezoidal sum before we go there. So we notice that we can use integrals to find area. It works well as long as there's a function where we can find the antiderivative or we're given a function. But often in life, sometimes functions are too complicated to find the antiderivative, or it could be that what we're given is simply data. So when that happens, we have to use an efficient method to estimate the area under the curve. And so what we've learned yesterday was that we can use a left-hand approximation, a right-hand approximation, and a midpoint approximation. Depending upon whether or not the function was increasing or decreasing, depending upon whether or not our approximation was accurate, how accurate it was. And we also noticed the more rectangles we used, the more accurate our answer was. So in this lesson, we're going to find a different method to approximate. So don't write this down, just bear with me for a moment. When we find the actual area under the curve, and you can do this on your calculator, and you will learn to do this in the next couple of days. But for now, just take my word. What you want to do is you want to find the antiderivative of this, which would be x cubed over 24 plus x. And we want to evaluate that from 0 to 4. And again, in a couple of days, I will give you more instructions on how to do that. But for now, just trust me that it's 20 over 3. And how I got that was I evaluated the equation at 4, the antiderivative at 4, and I evaluated at 0, and then I subtracted the 2. And we get a 6.6. Using a left-hand approximation, we see that the approximation is 5.75. Now, even if we used more rectangles, it would still be too low. We use a right-hand approximation. We see that the area is too high. We could average the two. But averaging the right and the left rectangles give us something called a trapezoidal sum. Notice that these look like little trapezoids. And we are using the trapezoidal formula. So recall from earlier math class that the trapezoidal formula, the area of a trapezoid is 1/2 times the height times B1 plus B2. In this example, our height is 1. Our height is 1 for each of these, and B1 would be this value, and this is B2. Notice also how they share B2. Okay, that's all going to become important when I show you the formula for a trapezoid approximation. And our answer when we use this approximation is 27 over 4, which is closer. It's still high, but it's closer than the other two were. And so from that, we develop the trapezoidal rule. And this is its formula. Notice this is our original, and our last is not multiplied by 2, But all the ones in the middle are multiplied by 2 because of what I showed you earlier, how they were sharing that wall, if you will. H is the width of the subinterval, so that would be b minus a divided by n, just like we were finding before. Now, this trapezoidal rule has a limitation. Write down the limitation. The limitation is this. It only works with even intervals. And I guess a better way of saying even intervals, all of your intervals have to be of the same width. Okay, this only works if you have intervals of the same width, which life is not always like that. So my suggestion is that unless you're given a formula, if you're given a table of values, to not use the trapezoidal rule, but just to use a sum of trapezoids. So this will work best if you're given a function and asked to integrate it from like 0 to 2. But the problem is that the AP exam hardly ever gives you that. Most of the time they will give you a table. Okay, so if we compare this with the midpoint, we see the midpoint is too low. So we have to recall this. If f is increasing function, then LRAM is less than the actual is less than the right-hand approximation. If it's a decreasing function, then the right-hand approximation is less than the actual is less than the left. We can conclude then that if f is concave down, then the trapezoid approximation is less than the midpoint, and if it's concave up, the midpoint is less than the actual is less than the trapezoid. This is important. There are questions on the AP exam that will ask you this, so it is really important that you commit this to memory. Okay, so here's an example where we're going to use the trapezoidal rule. It's going to work because we're going to have equal intervals and we're given a function. So the first thing we have to do is find our h. Remember, h is b minus a over n. So in this case, that would be 4 minus 2 over n. Well, I rewrote the function just to make my life a little easier. So finding h, we get b minus a over n, 4 minus 2 over 4, and that's equal to a half. So remember our formula. The 2 came from the outside, so this 2, that's part of the function. That 2 came from here. So the 2, these 2's are the same. That's where they came from. And this is the formula for a trapezoid. Okay? So h over 2, we found h to be a half. So h over 2 is going to be a fourth. Now, y0 is I'm going to take 2 from the bottom here, and I'm going to substitute that in. I'm going to substitute that 2 in to x squared, and I'll get 4. Because my width is a half, then my next point, I started at 2, the next one would be at 2.5. So I'm going to substitute 2.5 in for x squared. And the 2 that you're seeing is not the 2 from the outside, that is this 2. So because we're incrementing by a half, the next one would be 3. The next point would be 3. So it'll be 2 times 3, and then 2 times 3.5. And then the next point would be 4, so it would just be simply 4 squared. And then we would sum that up to get 37.5. Is it an underestimate or an overestimate? Well, if we were to graph 2x squared, what does that look like? So 2x squared looks like that. So it's concave up. And what did we say if it were concave up? Okay. Now we're going to use the trapezoidal rule again. This time we're starting at -1. We have to find h. So h is 3/4. So we're going to set it up. We're going to have h over 2. And we're going to start at -1. That's our y0. So we would substitute y0 into the equation. And we get -1 plus -1. The next one is going to be 2 times, because we started at -1, we're increasing by a fourth. I'm sorry, we're increasing by 3/8. The next one would be 0.25. We're increasing by 3/4. Sorry, we're increasing by 3/4. And again, we increase by 3/4. And we sum that up. Okay, so now we're going to do one where we have a table. Notice that my intervals are not equal. Because my intervals are not equals, I'm going to have to use individual trapezoids. So you're going to have to remember the formula for a trapezoid. Okay, so this is what this looks like. I was trying to sketch it, but you have to just forgive my rough drawing. So each of these is a trapezoid. So we're going to use each of these to find, we're going to find the trapezoid, the area of each trapezoid individually. So that first trapezoid, my y values, my B1 and B2 will be 1 and 2. My height is 1. For the second trapezoid, B1 is 2, B2 is 4, and my height is 2. For the third trapezoid, B1 is 4, B2 is 1, and my height is 1. And we would add those up to get an answer. Okay, so that's how we would do it if we have unequal trapezoids. And I was told by the chief reader of the AP exam, if you're given a trapezoidal sum on the AP exam, chances are it's going to have unequal intervals. So keep that in mind. So this is an example of something that you might see on the AP exam. I want you to notice the different processes that it's going to go through. So we're given this table and we're told that this is the velocity function. And they want you to show that the acceleration equals 0 at least once in the interval. Okay, so how are we going to do that? If this is velocity, remember its derivative is acceleration. And because I'm not seeing the acceleration function, I don't know any values of it, but I have to prove that it's 0, then maybe this is a good time to use the mean value theorem. Because if I can show that the average rate of change of the acceleration is equal to 0, then I can show that the derivative has to equal to 0. So if I want to show that the average rate of change is equal to 0, I could evaluate V of 4 minus V of 0 over 4. So that would give me the average rate of change, which would be the average acceleration. And we see that that is 5 minus 5 over 0. No, over 4, which is 0. And so because the average acceleration is equal to 0. Therefore, the acceleration has to equal to 0 somewhere along the line. What tells us that? The mean value theorem. So remember, if we're using the mean value theorem, we have to tell the conditions are met. So we have to say that since v of t is continuous and differentiable, how do I know it's continuous? Because differentiability implies continuity. So because it's continuous, and yes, you have to state both, and differentiable on the interval 0, 4, the MVT applies. And since the average rate of change, the average velocity, the average acceleration, acceleration is 0 on the interval A of t must equal to 0 on the interval. Okay, I ran out of room. But that's basically how we would prove that. Okay, now this one asks us to find the average rate of change of the velocity. On the interval 1, 4. I'm sorry, I was looking at that. I was like, didn't we just do that? But we're only looking at the interval from 1, 4. So the average rate of change on the interval from 1 to 4 would be v of 4 minus v of 1 all over 4 minus 1. So v of 4 is 5, v of 1 is 8, and 4 minus 1 is 3. So we get negative 1. What would be the units for that? Well, if velocity is given in meters per second, then that would be meters per second squared, because actually we found the average acceleration on that interval. But we don't know, so we'll just say units per time squared. Okay? So that's how we find the average rate of change. And finally, now let's do some Riemann sum problems. Now they want us to use the trapezoid with 4 equal subintervals from 0 to 4. And they want us to estimate x of 4. So we have to remember that PVA, if we have position, we take the derivative, we get the velocity, we take the derivative, we get the acceleration. Well, the opposite of that is true. If I have acceleration and I take the integral, I get velocity. If I have velocity and I take the integral, I get position. So when I'm using a trapezoidal rule, I am approximating, right? I'm approximating the integral of the velocity, which is going to give me position. Okay? So, but this has equal intervals. So this is not really fun to do, but we'll do it. We could use the rule or we can use individual triangles. So because it's equal, I'm just going to use the rule. So the rule would be, to find h, would be 4 minus 0 over 4. So h is 1. So the trapezoidal approximation at 4, the 4 indicates how many subintervals we're taking, by the way, would be 1/2 times h. And since h is just 1, that's going to come on the outside. And then it would be 5 plus 2 times 8 plus 2 times 15 plus 2 times 10 plus 5. And I think that's going to give me 38. what is that? 5 plus 16 plus 30 plus 20 plus 5. So what is that? That's 10, 30, 60, 46 times a half, so 38. But 38 is not my answer because I started at x of 0 is equal to 2. I have to add that 2. So my answer is x of 4 is equal to 40. And some of this will make sense after we teach PVA. But I just wanted to show you a trapezoidal rule. Okay? All right, that's it for this. Your homework is a class kick, and I will see you guys tomorrow. You now have 4 methods to approximate the area under the curve. Remember, approximating the area under the curve is approximating the integral. So you should be able to use left ram, right ram, midpoint, and a trapezoidal sum. Also recall that the trapezoidal sum, the formula only works when you have equal intervals. So I always say it's best to just use individual trapezoids because that works all the time. Then you also should know under which situation will you have an over approximation or an under approximation. So if a graph is increasing, a left Riemann sum would give you an under approximation, while a right Riemann sum gives you an over approximation. Things like that you need to know for the AP exam and for the test. Please do your homework and have a great day. Thank you for watching.